Imagine that this fair die has already been rolled. The result exists, but it is hidden. Before we lift the cover, what can probability tell us about that result? We write that the probability of a 5 being rolled is 1/6, since the dice has 6 faces. What does that 1/6 really mean? If probability is interpreted as frequency of occurrence, 1/6 describes a long-run frequency of 5s across repeated rolls of the same experiment. However, if we interpret it through a degree of subjective belief, it describes our uncertainty about this particular hidden outcome. We assign an uncertain probability to a specific outcome. These are different interpretations of probability, but both use the same mathematical rules developed in this chapter. This lesson and the broader tutorial will draw from both interpretations and see how we can use these to interpret outcomes such as dice being rolled and other examples. Specifically, we are going to discuss elements of probability such as events, probability mass, and independent pairs and conditional factors. Let's start with data we can observe. Probability has two useful roles. It can summarize repeated observations, and it can distribute uncertainty across outcomes that we have not observed yet. Both roles use probability distributions. Let's look at the first approach, which is the frequency of occurrence. We are going to repeat the same experiment where we record whether each roll is even and ask for the proportion or the fraction of even rolls observed so far. After 12 rolls, we observe 7 even outcomes, and 7 divided by 12 total rolls is about 0.58. After 60 rolls, that estimate changes to 31 over 60, or about 0.51, and with 600 rolls, the estimate approximates to about 0.5. For repeated rolls of a fair die, the probability of an even roll tends to settle near 1/2. The observed count still comes from data, as here probability describes a stable pattern we expect across repetitions. Now let's change our approach. Instead of summarizing past rolls, we describe a result before we see it, through a measure of uncertainty. The blank face stays unobserved, but not without value. The die has one result. Our current information does not identify which of the 6 values it is. The empirical estimate becomes a distribution over the possible result. Before the outcome is observed, the 6 equal bars record the uncertainty that remains in our estimate. This is the probability mass before observation. So for a fair 6-sided die with a face x, every value from 1 to 6 receives a probability of 1/6. All outcomes probabilities summed together equals 1, meaning that we capture all possible outcomes and that this is a valid probability distribution. Let's begin by a brief review of set theory and basic elements of probability. A set is a collection of objects or elements. Here we have 2 events represented as sets. So let A be the event 2, 4, and 6, and let B be the event containing 4, 5, and 6. 2 belongs only to A, while 5 belongs only to B, and 4 and 6 belong to both. 1 and 3 lie outside both events A and B, but it is still, of course, in the world of possible outcomes. Which region do you think represents A union B, or alternatively, which region represents the event A or B? Decide which phases survive, and remember that OR includes the overlap. So the union contains 2, 4, 5, and 6. The blue region marks A only, orange region marks B only, and purple marks the shared part. Although outcomes 4 and 6 form part of both A and B, it is not entered twice simply because it satisfies 2 descriptions. The union is still a set, and one of the properties of a set is that each outcome can only appear once. Now for the intersection of these events, called A and B. This answers the question of which elements are shared by both events A and B. This leaves only 4 and 6, since these are the only outcomes that satisfy both conditions. The complement asks when an event does not occur. The complement of event A means that the even phases are excluded, so the remaining events are 1, 3, and 5. A and its complement therefore cover the sample space without overlap. That is, all the events in A combined with all the events not in A. describe the entire sample space omega. Next, let us define a probability space. For this explanation, let's keep event A for now. The probability space is a fundamental framework for expressing a random process, such as those we are interested in. Using this framework, we are able to describe which outcomes are possible, which event questions we are able to ask, and what outcome probability each event receives. The faces of event A join 1, 3, and 5 inside the sample space omega. Each individual face is one outcome, written lowercase omega. Each outcome can be thought of as a complete description of the state of the world at the end of the experiment. Together, the 6 outcomes describe every possible result of this experiment. Selecting 2, 4, and 6 groups outcomes into A. A is therefore a set of outcomes, and it belongs to the event space F, which is a subset of all possible sets of outcomes known as events. It represents the collection of subsets of possible interest to us. For this small example, we can consider the event space to contain the full power set, where the event space F equals the power set of omega. The power set is the set that contains all the possible subsets, or in this case, all possible outcomes or roles for any number of the die from 0 through 6. 4 events are shown here: the empty event, A complement, and omega. These 4 rows, or separate elements, are examples contained in F. In reality, F has 64 events, but we won't show them all here. The probability measure P maps each allowed event to a number from 0 to 1, which represents its probability. The empty event is assigned 0. A and A complement are assigned 1/2 each, since in this example, both describe equally likely events. And since omega is the complete sample space, it is assigned 1. The mechanism is now complete. We next ask which rules make the event collection and its probability assignments valid. F answers which events are allowed, while P assigns a mass or a probability to those events, and the probability axioms, or sigma algebra, constrain the assignment. That is the whole framework. Now we can test each part on the die. A sigma algebra is an event collection closed under the required set operations. In plain English, this just means a sigma algebra is all valid questions or events we are allowed to ask about. Let's begin with A, which is in the event space, using the same even faces as before. May event space F contain A but omit its complement? If we allow the question, did A occur, must we also allow, did A not occur? The short answer is no. Logically, if we can measure a specific event A, we should also be able to measure its opposite. This is referred to as closure under complement. The 2 events are disjoint, and together they cover the complete sample space omega. Hopefully you can see that A and A complement covers the entire sample space, as all 6 possible outcomes are accounted for. Closure keeps logical operations inside the domain of P. Without it, a basic question could be measurable, while its opposite is not. But complements are only one way we might build new events from old ones. We also might want to combine events. So we need one more closure rule. If we can take a countable collection of allowed events and form their union, that union must also be an allowed event. Here we see an example where the finite instance A, union A complement, equals omega. This rule applies to any countable collection of events. So the event space tells us which questions we may ask, but how do we answer those questions? That is done via the probability measure. Specifically, the probability measure takes in events from the event space F and assigns it a probability. That is a number between 0 and 1. Here we consider 4 events: the empty set, A, its complement, and the sample space omega. With the probability measure, we can assign probabilities to each of these events. The empty event receives a 0 probability. The even event, A, and its complement receive 1/2, and the full sample space, omega, receives 1. What is important to realize is that these values are not arbitrary. They must obey 3 axioms developed by Andrei Kolmogorov in 1933. An axiom is a statement or a rule that people accept as true without any proof. The first is non-negativity. Each probability must lie between 0 and 1. Negative probability has no meaning, and no event can contain more than the total available mass. So practically, we cannot assign a negative 50% chance of it raining tomorrow, just like how we cannot assign a positive 120% chance of it raining tomorrow. All that the non-negativity axiom is really saying is that probabilities are bounded between 0 and 1. Second, the probability of the full sample space is 1. This means that something in the full sample space has to happen. When we roll a die, it must land on one of its 6 faces. And for a fair die, each of the 6 outcomes are equally likely with a probability of 1/6, and those 6 probabilities add up to 1. Third, if 2 events cannot happen at the same time, we can simply add their probabilities. For example, a die cannot be both even and odd. These 2 events are disjoint, which means they share no common outcome. So the probability of rolling either an even or an odd number is just the probability of even plus the probability of odd. This is the axiom of disjoint additivity. This works for any countable collection of pairwise disjoint events, which is just a way of specifying events that share no possible outcomes. The axioms define a valid probability measure. Do not try to memorize these axioms and their definitions. Rather, try to understand and internalize them. Over time, it will become second nature. And using these axioms, we can now derive several useful properties. We'll derive each property using a set diagram. The first property is monotonicity. If we have a set A inside a set B, then every outcome in A is also in B, while B may contain additional outcomes. It follows that the probability of A cannot exceed the probability of B. This is the property of monotonicity. If A is a subset of B, then the probability of an outcome of A occurring will always be less than or equal to the probability of B occurring. It is at most the same as the probability of an outcome of B occurring. Now, let's let the events A and B overlap. The part that overlaps, or the intersection, lies inside A and B. This means that the intersection is a subset of both A and B. So by the property of monotonicity, its probability cannot exceed either event probability. Therefore, it cannot exceed the smaller of the 2 events. Now for the next property. If we add the probabilities of A and B, which region, if any, do we count twice? Since the overlap belongs to both events, the sum of both events count that overlap twice. Therefore, when we add 2 overlapping events, we have to subtract that overlap once. This is called the inclusion-exclusion rule. And notice that if the events don't overlap, that last term is 0, and we're back to the disjoint case we saw before. Let's return to the events where they were overlapping before deriving the next property. This overlap also gives us a useful upper bound. So remember, when we calculate the exact probability, we subtract the overlap because we originally counted it twice. But if we just ignore that overlap, the sum of events may be too large, but it can never be too small. This gives the union bound, and that is the probability of the union of events A and B is at most the probability of A plus the probability of B. This upper bound becomes an equality, when A and B are disjoint. This is useful because even when we don't know how events overlap, we can still put an upper bound on the probability that any of them occurs. Let's discuss the complement next. A and its complement divide omega into two disjoint parts. They contain no common outcomes, and therefore there is no overlap. Since everything in A plus everything not in A describe the complete sample space, their probabilities add to 1. Therefore, it follows that the probability of A complement equals 1 minus the probability of A. The same argument applies to a finite partition, and a finite partition is a division of a sample space into a specific, countable number of non-overlapping, mutually exclusive subsets. Together, they cover the complete sample space. Each outcome belongs to exactly one cell, so the probabilities add to 1, and they cover the complete sample space. Here's a quick recap over the properties we just discussed along with their equations. Similar to the probability axioms we discussed earlier, do not try to memorize these, try to internalize them. As you work more and more with probability, these properties should become evident to you if they are not already. Next, we'll discuss the dependence and independence of events. Two events are independent when learning that one event occurred does not change the probability of the other having occurred. To illustrate this concept, we can begin with two rolls of a sphere 6-sided die. Each cell represents an ordered pair. In this grid, the first coordinate, x1, corresponds to the first roll, and the second coordinate, x2, corresponds to the second roll. There are 36 equally likely pairs, so cell counts represent probabilities. Let A be the event that the first roll is even, and let 3 of the 6 columns satisfy that condition. That gives 18 cells out of 36, so P of A is 1/2. Let B be the event that the second roll is greater than 4. 2 rows satisfy that condition, so the probability of B is 12 over 36, or 1/3. 6 cells satisfy both A and B, so the probability of the intersection of A and B is 1/6. That is, the probability of the first roll being even, as well as the second roll being greater than 4, is 6 over 36, or 1/6. Notice that the probability of A, 1/2, multiplied by the probability of B, 1/3, gives us the probability of the intersection of A and B, which is 1/6. This forms the first independence equation. Two events are independent if the probability of the intersection of A and B equals the probability of A times that of B. We can express the independence of two events with conditional probability as well. If we restrict the grid so that only B, or the second roll, is visible, 12 cells remain. 6 of those cells satisfy A, so the probability of A given B is still 1/2. Learning B's outcome did not change the probability of A. If observing the outcome of one event does not have any effect on the other, those two events are independent. So far, we have tested independence between two events. But how can we check independence with 3 events, let's say A, B, and C? The 2-event example now leaves the screen. For 3 events, we must check more than one relationship. We start with each pair, A with B, A with C, and B with C. If every check passes, the events are pairwise independent. This still does not prove that all 3 events are mutually independent, however. To see why, consider 2 independent fair bits, x and y. Each bit can be 0 or 1, and each value is equally likely. X defines the rows and y defines the columns. The grid contains 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. Each state has a probability of 1/4. These 4 cells contain every possible bit pair. We can define A as the event that x is 0, and we can define B that the event y is 0. And then we can define C as the event that x and y are equal. The labels show which events occur in each state. Do A, B, and C pass every pairwise independence check? Think about that for a bit. Each event occurs in 2 of the 4 states, so each event has a probability of 1/2. Any pair occurs together in exactly 1 state. Each pairwise intersection therefore has a probability of 1/4. 1/4 equals 1/2 multiplied by 1/2, so every pairwise independent check passes. Now consider all 3 events together. Their intersection has a probability of 1/4. All 3 events occur together only in the 0,0 state. Mutual independence would require the product of the 3 individual probabilities, that is 1/2 multiplied by itself 3 times would equal 1/8. Now 1/4 is not 1/8. The events are pairwise independent but not mutually independent. Event C depends on A and B together, so knowing A alone or B alone does not determine C. Knowing both determines C completely. A dependency therefore appears when we consider all 3 events together. Let's next investigate conditioning. We'll return to our previous events A and B on one die only. Suppose one die was rolled and we learned that an outcome in B occurred. Which outcomes remain possible? B is a set containing 4, 5, and 6. Of course, the outcomes 1, 2, and 3 are now impossible under this condition. So only 4, 5, and 6 remain. If we normalize their original probability masses, each surviving outcome is assigned a mass of 1/3. Within the event set B, outcomes 4 and 6 also belong to A. The original mass is 2/6, which is the probability of the intersection of A and B. Together, all outcomes in B have an original probability mass of 3/6. So what is a conditional probability then? The conditional probability of A given B is the probability of their intersection divided by the probability of B. We're restricting our attention to cases where B happened and asking what fraction of those cases also belong to A. We already know the numerator is 2/6 and the denominator is 3/6. This ratio simplifies to 2/3. In other words, among the cases where B happened, 2/3 also satisfy A. The 3 conditional masses now add to 1, and 2 of the 3 equal masses also belong to A, so P of A given B is 2/3. This can be thought of as conditioning, which brings us to the chain rule. Repeated conditioning gives us the chain rule of probability. Let's consider an urn with 4 purple balls and 2 grey balls. In this example, we will draw 4 balls without replacing any. Ask yourself, what is the probability that all 4 draws from this urn are purple? Before the first draw, 4 of the 6 balls are purple. After the first draw, 3 purple balls and 2 grey balls remain. Now, given the first draw, the next probability of drawing a purple ball is 3/5. Given 2 purple draws, 2 of the 4 remaining balls are purple. Given 3 purple draws, only 1 of the 3 remaining balls is purple. Multiplying all 4 factors, that is all 4 probabilities of drawing purple, gives 1/15. Therefore, there is a 1 in 15 chance of every ball drawn being purple in this example. Moving beyond the example, let's try to derive the mathematical formula of the chain rule of probability. The specific 4 event chain moves up so we can expect its terms. A1, A2, A3, and A4 means that the first, second, and third, and fourth draws are purple. The first factor is unconditional, and each later factor is conditional on all earlier purple draws. This product, or rather this chain, does not assume independence. The changing factors represent the dependencies created by sampling balls from the urn without replacing any. So can you spot the general formula? For n ordered variables, the joint probability of x1 through xn equals a product of conditional probabilities. The factor corresponding to xi gives a probability of xi given all earlier values. The chain rule shows that we can break a joint probability into a sequence of smaller conditional probabilities. Probabilistic graphical models take this idea further. The graph tells us which variables each probability actually depends on. This can let us describe a large joint distribution using a collection of much smaller conditional distributions. Thank you for watching. In the next lecture, we'll look at section 2.2, which is random variables. Please leave any feedback in the comments below and